Hello everyone, welcome to this lecture on phases of a compiler. So let us see what are the major parts of a compiler. Now when we talk about a compiler, we usually think of it as, say, something like this, a black box where you give as input a source program and you get it out as output a target program. Okay, so what happens here inside the compiler? Okay, we have not seen what goes on inside this. So if we look at the things that goes on inside the compilation process, then we can divide this into two main components or two main parts. The first part is known as your analysis. And the second one is known as synthesis. Synthesis. So what is this analysis and what is this synthesis? So in the analysis, what we have is we are given this source program in a high level language, and the analysis breaks it down into its smaller parts, okay, or the components of the program. Then these parts are grouped together. These are grouped together to form a structure according to the grammar of the language. So you have the grammar of the language. So the components or the parts of the program is arranged in the form of a grammatical structure, which is in form of a tree, as we will see later on. And then from the structure, we get an intermediate representation. We get an intermediate representation. So all these things takes place during the analysis phase. Okay, so you take as input a source program. This is broken down into its smallest components or parts, which is again grouped together according to the grammar of the language, and from there it is converted into an intermediate form. All right, and if during the process any errors are found, then those are reported. Now the synthesis phase will now look at the intermediate output of the analysis, which is the intermediate code, and then from here it will convert it into the target code. It will convert it into the target code. So whether it is some other programming language or some other intermediate language or some machine language, the synthesis part will do the conversion into the desired target program. So this is the analysis and the synthesis. That is the two part things that takes place inside the compiler. And another term for analysis is it's also known as the front end. The front end, and the synthesis is known as the back end. This is the back end. Okay. Now, once this is done, okay, now let us look into the different phases of the compiler. So these are the two, analysis and synthesis. These are the two main components. Now these analysis and uh, synthesis can be broken down into a number of phases. So you have the first phase is called the lexical analysis phase. Then you have the syntax analyzer. Then you have the semantic analyzer. Then intermediate code generator. So the first four phases of compilation, these fall under your analysis phase. And the remaining three, machine independent code optimization, code generation, and machine dependent code optimization, these are under your synthesis phase. Okay, so if you look at this again, you will see that we have, you can see first phase is the lexical analyzer phase or lexical analysis phase. Okay. Then this is also termed as scanning. Then you have the syntax analyzer phase. Okay, so it takes the input, which is the output from the first phase. This goes as input to the next phase. From here again, now it gives an output. This goes as input to the next phase. And the process continues. So you have syntax analyzer, semantic analyzer, intermediate code generator, then machine independent code optimizer, code generator, and then machine dependent code optimizer. So we'll go through each and every phase of this compilation process throughout our course. Now, in addition to these phases, there are two other things which are important. That is the symbol table. Okay, this is a data structure which is used throughout the different phases of the compilation. Most of the phases they use, in fact, all the phases use the symbol table. And there is another routine here called the error handler. So the error handler is responsible for handling whatever error occurs during all these different phases. So if there is any error in the lexical analyzer phase, it will be handled by the error handler here. Similarly, for syntax analyzer, similarly for machine dependent code, all of these is handled by the error handler. So now let us go through each and every phase in brief. So we start off with the lexical analyzing phase. So the first phase is called the lexical analysis, and or anything you want to call it. The lexical analyzer is the code, and the phase is called lexical analysis. This is also known as scanning. All right, and then in the lexical analysis phase, what happens? You have the lexical analyzer here, and what goes as input to it is the sequence or the stream of characters in your program. So in your source program, the source program is considered to be a sequence of characters. This goes in, and what comes out is a sequence of units which are called lexemes. Okay, what you get out of this is a lexeme, and then these lexemes are organized by the lexical analyzer into something called tokens. So let me explain this with an example. I think I have in the next slide an example. Okay, so here you see, you can see here, this is a string. This is a statement of your high-level language program. So you have position assigned initial plus rate into 60. So this is one line of your program. So this goes as input to your lexical analyzer. And what the lexical analyzer does is that it breaks up this string into smaller units, which are known as lexemes. Okay, so what are the lexemes here? We have these lexemes. So here position here is a lexeme. This is a lexeme. Initial is a lexeme. This plus operator is a lexeme. Rate is a lexeme. this is a lexeme and this 60 is a lexeme. So from this statement, total we get 1, 2, 3, 4, 5, 6, 7, 7 lexemes we get. Now these lexemes are arranged in the form of something known as tokens. Something known as tokens. T-O-K-E-N-S. Tokens. So what are tokens? Tokens are just some grouping of these lexemes. Okay. So first let me write for the ones which do not need any grouping, like say assignment operator. This is a token by itself. Okay. Then I have plus. This is a token. Multiply. This is a token. Okay. These three are tokens. Also, I have position, initial, rate, and 60. These are also lexemes. Now, what are the corresponding tokens for this? Now, if you look at position, initial, and rate, these are nothing but variables. So, they are known as your identifiers. So, we will represent the identifier tokens in this manner. We'll write first that it is an ID. Alright. So, this is for position. So, we are writing the token for position. So, for position, it would be something like this, ID and 1. What is this 1? This 1 is nothing but, this is the location in the symbol table where position appears. Okay, so ID 1. So, this is the token for position. Similarly, for initial, I have, that is also an identifier, and its position in the symbol table is 2. So, this is here. Okay, then for rate, I have ID 3. So ID 3, it is pointing to this 3. 3 means here, rate appears here. So ID 3. So these are the tokens. So in general, you can say you can represent a token as something like this: token name, comma, attribute. Token name, attribute. So what this lexical analyzer will do is that it will take one lexeme, convert it into the token. So position, it has made this here. This one for assignment, this is for initial, then and so on. And also what it does is that the moment it finds a new identifier, it will insert it into a table known as the symbol table. Okay, and it will, along with the the name of the variable, it will add some more information, like what is the data type of this variable, what is the value it is holding, and so on. Okay, so the token and the lexeme. So we'll see more about tokens in the coming lectures. So this is the work done in the lexical analysis. So this is another example. This is a program. Okay, this is a program in some language. So you can break it out into. So what you see here. So what you see here is these are your lexemes. These are not tokens. These are lexemes. Okay, so from here now you can get your tokens. So this is what is done in the thing. So in lexical analysis, we saw that it is, you get the tokens and the identifiers are added to the symbol table. Now, one thing I missed out is that there was this value 60. There was this value 60 out here. Now, 60 is a constant. It does not enter into the symbol table. We will not put a constant into the symbol table. Okay. Instead, there can be another table known as a literal table. Literal, literal table, where 60 can be entered. And you can have a token for 60, something like this. Or you can have a token for 60, something like this, because 60 is a number, so I can write like this. Number is the name of the token, and its attribute, the value is here, is 6. Okay, so you can write it like this. More about this in later class. So this was your lexical analysis. Now next comes your syntax analysis. So in the syntax analysis, what the syntax analyzer gets is the sequence of tokens. The sequence of tokens. Now, what the syntax analysis use is that it uses the grammar of the language. So for any programming language, the rules of the syntax is represented using a grammar, and this grammar is known as your context-free grammar. Oh, sorry. Context-free grammar. All right. So in the context, using this context-free grammar, it will check whether this sequence of tokens that has arrived from the syntax, semantic, and from the lexical analysis, whether it meets the syntax of that particular grammar or not. If no, so if it does not meet the rules of the grammar, then what you get is you get error message. And if yes, then what you get again is a structure which represents the sequence of tokens in the form of a tree, which is known as the parse tree. Parse tree. Okay, so you can see here, this is the grammar for a particular language. So you can see statement here. What is statement? A statement can be a for statement, an if statement, an assignment statement. Similarly, a for statement can be something like this, starts with for, parenthesis, then expression. Okay, this is your C, basic C syntax. So you can have a grammar for the language written in this manner. Now, what the syntax analyzer does is that this is our same statement. Okay, position is equal to initial plus rate into 60. Okay, so now from the tokens that it received, the syntax analyzer received the tokens. These tokens, it arranged it in the form of a tree like this, and at the same time it has also maintained associativity of the operators, then precedence. You can see multiplication is done before plus. So all these rules are maintained. So what you get, this structure that you can see here is the parse tree. Now the next step is your semantic analysis. So the semantic analyzer, it takes the information that is there in the symbol table, and it takes the syntax tree, okay, and then it checks whether the program is semantically correct, okay, based on the definition of the language. Like, say for example, okay, it does things like type checking. So type checking is done. So you have done A plus B. Now whether A and B are of the correct type or not, okay, it is grammatically correct. I can write a statement like this. This can be my parse tree, okay. But whether this is grammatically correct, but whether it is semantically correct, that is whether the meaning of this operator is proper or not. Like, say A can be an integer, whereas B can be a string. Okay, so syntactically it is correct, but semantically it is not, because you cannot add a string with an integer. So the semantic analysis does this. It also takes care of things like type conversions, coercions. So things like coercions, that means automatic type conversions, like widening and narrowing. So all these are handled by the semantic analysis. So what you get as output of the semantic analyzer is something like this. It is the same parse tree, as you can see. It is the same parse tree that it gets from the previous phase. But here you can see the 60 is an integer, and if we assume that position, initial and rate are all floating point numbers, then the semantic analyzer adds this operation int to float to convert 60 to a floating point number. Okay, so it does these automatic conversions. So what you get here now, this is the semantically augmented syntax tree. Okay, so this is your semantic analyzer. Now, once this is done, once you have the semantic analysis, in the semantic analysis, all type checking and everything has been done, grammatically correct. All the words of that program are according to the language specifications. Now, in the intermediate code generation, the compiler, it generates a machine-like. Okay, this is not exactly the machine code, but it is machine-like. Machine-like language. It uses a machine-like language to represent the program. Okay, so why does it need to do so? Because it is easier to convert from a high-level language directly to convert to machine language. Okay, it's difficult. Okay, and also the machine code generated directly may not be so efficient. So to bring in efficiency and ease of use, we first convert to an intermediate code. First we convert to an intermediate code, and then we convert it into machine code. So when you see Java, you'll realize that there is something called a bytecode, which is nothing but it's a machine independent representation of the high level code. And then this bytecode is converted into machine code by the interpreter. So in intermediate code generation, there are different types of intermediate codes. One is the syntax tree is also a kind of a intermediate code, the syntax tree. Then there are other representation like tree address codes. Tree address codes are there. All these are different types of intermediate code. Okay. So two features are to be taken care of. Two important things are there. One is it should be easy to create. This intermediate code should be easy to create, and it should be easy to convert to machine code. You should be able to convert it to machine code easily. So these are the two important points about your intermediate code. Okay. So you can see this is an example where we have here, you can see we have an intermediate code. So this does not look like machine code. At the same time, it is more close to your machine code. It is closer to your machine code than compared to your high level language code. Okay, so this is an example. So next phase is your code optimization. So here we got, as you can see here, this is our intermediate code. Okay, our initial statement was like this: position is equal to initial plus rate into 60. From here, we got an intermediate code, something that looks like this. Now, Code optimization, what it does is that it optimizes the code, that intermediate code that has been generated, so that it becomes more efficient. So if you look at this, intermediate code, so you have an operation here, int to float 60. So that means you're converting from integer to floating point 60. So instead of having this operation, you can directly write it as 60.0. Okay, so this will be removed. This can be removed. Then next you can see this T3 variable is not used anywhere. It is just used for temporarily holding this value, holding this value and then assigning it to ID1. So this we can remove. So T3, we can just remove it. So the same thing, what is here in this intermediate code, you can get a optimized version of this intermediate code by writing it like this. So 60.0 into ID3. What is ID3? ID3 is the rate. So this is 60 into ID3 is stored in T1. So T1 is stored in this. And what is ID2? This is ID2. ID2 plus T1 is being stored in ID3. Oh, sorry, ID1. ID1. So this is ID2. This was ID3. So this is the same code doing the same work, but it is optimized. So code optimization does things like this, and it is an optional part. It's not always required. So this is an optional phase. If you want quick and fast, you don't want optimization, then you can skip this. Certain compilers can skip this optimization. And the final phase is your code generation. So the code generation takes this optimized intermediate representation of your source program and then it converts it into the target language. So you have your optimized intermediate code. Okay, so this is converted into the target language. And if this target language code is your machine language, if this is your machine language, in that case you have to see the registers, what registers to use, okay, which memory locations to use, which instructions to use. All these are decided in the code generation phase. And there can be a lot of things that can take place during code generation, like we want to make efficient use of registers. Okay, we want to reduce number of memory operations. We'd like to see which instructions we can omit. Okay, by replacing some of the instructions. Okay, so these are again some considerations that has to be taken care of in code generation. So these were all the different phases of your compilation. So you can see this was your this diagram shows the intermediate code that we got. Okay, then this was optimized. We got this optimized code. From the optimized code, we now mapped it to the machine code for a specific machine. So machine code will be only for a specific architecture. So as you have studied in your computer organization and architecture class, okay. So depending upon the architecture, there will be different registers. So which registers you are going to use? Like here, we are using registers. Here we are using something else. So these may be memory locations. Okay. So different addressing modes are being used. So all this is your output of your compiler, the machine. So that was all about phases of a compiler. Now just in short, two things. That is your symbol table management. Okay, as you saw in the first diagram that you had two things: symbol table. We had symbol table and we had error handling. These were two additional. These are not phases of compilation, but it is additional. So in the symbol table, okay, it is a data structure which is used throughout the compilation process, and it is filled in at different phases. So initially it is filled in during the lexical analysis phase, and then at different times, different phases, okay, the symbol table is filled in with different values. Okay, and the it is a it is a data structure which contains one record for every variable that is present in the program, in your source program. Now the main design consideration is that it should be fast. You should be able to retrieve uh, fast retrieval of data. Okay, you should be able to find a record quickly, and also you should be able to store also fast. Store fast. It should be easy to enter and easy to retrieve. So we'll discuss more about simple tables uh, slowly. And the last thing is your error handling. Like I had already mentioned, the errors can occur in different phases of your compilation. So all the errors that occur during different phases has to be handled. So there are error handling routines. There are error handling routines in your error handling routines are there in the compiler, which will take care of errors in all phases. In every phase, it will handle the